Okay, let's start with the basics. What exactly is load balancing? It's all about distributing incoming traffic across multiple servers instead of having everything funnel through a single point. Imagine you have a website that gets tons of visitors at once. Without load balancing, one server might get completely overloaded and slow down or even crash. Load balancing prevents this by intelligently routing users to the best available server, ensuring everyone gets a good experience and keeping things running smoothly. Okay, so let's talk about why load balancing is such a big deal in today's apps. Basically, most modern applications aren't just running on one server, they are spread out across many. Without a system to manage that traffic, things can get really slow and unreliable. Imagine trying to check out at the grocery store with only one cashier. It would be chaos. Load balancing ensures that requests are distributed efficiently across multiple servers, keeping your application fast, available, and able to handle increasing demand. Okay, let's talk about the different types of load balancers. First, you have hardware load balancers. These are specialized appliances that really handle traffic distribution powerfully. Then there's software load balancing, which is running on regular servers and offers a lot of flexibility and cost savings, especially in cloud environments. Cloud load balancers, provided by services like AWS or Azure, are fully managed and super easy to scale. And finally, we have Layer 4 and Layer 7 load balancers. Layer 4 just looks at IP addresses and ports for routing decisions, while Layer 7 dives deeper into the content of the request to make even more intelligent choices. Okay, let's talk about the difference between Layer 4 and Layer 7 load balancing. Think of it this way: Layer 4 is like a traffic cop checking ID in ports, fast and simple, but doesn't know what you're doing. It just directs you to the right building based on your address. Layer 7 goes much deeper. It actually looks at what's inside the packages being sent, examining things like URL and cookies. This allows it to make smarter routing decisions. For example, sending users who request specific images to a server that's best equipped to handle them. Layer 7 is more powerful, but also requires more processing power. Okay, let's talk about Layer 4 load balancers. These are really efficient because they operate at a lower level, the transport layer. Essentially, they look at the IP address and port number of each incoming request to figure out where it should go. They keep track of sessions so they can route requests back to the same server for repeat users. Because they are quick to make decisions, they are often used in situations where speed is critical. Think about a website handling lots of traffic simultaneously. Okay, let's talk about how Layer 7 load balancers work. They're a step up from the more basic Layer 4 ones. Instead of just sending traffic based on IP address and port numbers like a simple postal service, Layer 7 examines the actual content of the request. Basically, it understands what the user is asking for. This means they can route requests to different servers depending on things like the URL being accessed or even the type of data being requested. They can also maintain user sessions using cookies and manipulate HTTP headers. Because of this advanced analysis, Layer 7 load balancers give you a lot more control and flexibility over how traffic flows through your infrastructure, but it does require a bit more processing power. Okay, let's talk about round-robin load balance. It's a really common concept you'll see in interviews. Imagine a group of servers handling website traffic. Round-robin just means each server gets its turn to handle the next request, one after another. It's like a rotating door. They cycle through in order. It's super easy to set up and understand, but it's important to know that if one server fails, the others keep working without any automatic adjustment. So, while simple, it doesn't take into account how busy each server actually is or how well each is performing. Okay, let's talk about least connections load balancing. It's one of the most fundamental algorithms out there. Essentially, it's super straightforward. When a new request comes in, the load balancer just picks a server that currently has the fewest active connections open. It's really easy to implement, which is part of why it's so popular. However, you need to be aware of its limitations. It doesn't take into account things like how busy a server actually is or how long requests might take to process. So while simple and quick, there are scenarios where other algorithms might be better suited. Okay, let's talk about IP hash load balancing. This method is pretty simple to understand. It essentially uses a client's IP address as a key to determine which server handles their request. Think of it like assigning each customer to a specific cashier. They always go to the same person. That consistency can be great for things like caching, because if a user returns, they'll likely be routed back to the same server where their previous data was stored. However, there's a catch. If many clients share the same IP address, say all coming from the same office network, one particular server could get overwhelmed. That's called a hotspot, and as more and more users connect using different IP, this method might not be ideal for scaling your system effectively. Okay, let's talk about weighted round-robin load balancing. It's an improvement over the basic round-robin approach. Standard round-robin just gives every server an equal slice of the traffic, which isn't always ideal if some servers are more powerful or have less work to do at any given time. Weighted round-robin takes this into account by assigning each server a weight, essentially an estimate of how much capacity it has. So, a higher weight means that server gets more requests routed to it. It's like giving bigger slices to the servers that can handle them better. This dynamic adjustment based on performance helps ensure your application remains responsive and efficient. Okay, let's dive into sticky sessions. Think of it like this. Sometimes you want to make sure a particular customer always talks to the same person in a store, right? Sticky sessions do something similar for web applications. They're about ensuring that all requests from a specific user are consistently sent to the same server during this session. This is really important when your application needs to remember things about a user, like whether they are logged in or what items are in their shopping cart. They typically use cookies to track which server handled the initial request, so future requests from that user get routed back to it. It's a common interview topic, so be prepared to explain how it works and its potential downsides, namely, if one of those servers goes down, all sessions for that user are lost. Okay, let's talk about session persistence and load balancing. Essentially, it's all about making sure a user always gets routed to the same server during their entire session, like when they're shopping online or managing their accounts. Why do we need this? Well, if you refresh a page without persistence, you might suddenly lose your cart contents or have to start over. It's most useful when your application relies on remembering things about a user across multiple requests, like their shopping cart or profile details. However, remember that adding persistence means you're relying on something like Redis or a database, which can add some overhead and impact performance, so only use it when it's truly necessary to keep the user experience smooth. Okay, let's talk about health checks. They are absolutely vital in load balancing. Think of them as regular "Are you okay?" probes that the load balancer sends to each server it manages. It's like a little automated heartbeat monitor. These checks can verify if the server is responding with a good HTTP status code, or if it's even reachable on the network, things like TCP connections and whether specific parts of your application are working correctly. They help prevent traffic from getting routed to servers that aren't actually serving requests properly, which would obviously be terrible for users. There are different kinds too, like passive checks, which are less intrusive, and active checks, which actively test the server's functionality. Okay, let's talk about health checks and load balancing. They are super important. There are two main types, active and passive. Active checks are like a quick pop quiz for each server. The load balancer sends a request and expects an answer. If it gets nothing back or something unexpected, that server is immediately taken off duty. It's a reactive approach, meaning it acts asterisk after asterisk a problem. Then we have passive health checks. These happen less often, like during quiet periods. Instead of kicking the server out right away, the load balancer keeps sending requests and watching for problems over time. This is more forgiving, giving servers a chance to recover, but also requiring really good monitoring to catch issues before they seriously impact users. Let's talk about what happens when a backend server doesn't pass its health check during load balancing. It's a really important scenario that often comes up in interviews. Basically, the load balancer sees the server as unavailable and immediately removes it from the rotation of servers it's distributing traffic to. It then smartly redirects all incoming requests to the other healthy servers in the pool. And here's the clever part: many load balancers will even try to automatically check on that failing server a few times, hoping it recovers. It's vital that you alert operations when this happens so they can investigate and fix the root cause of the problem. Think about how frequently you run these health checks and what they actually test. That's key. Okay, so let's talk about SSL termination. It's a really important concept in load balancing. Basically, we don't want every single server in our application stack handling encrypted HTTPS traffic. That would be a lot of work. So, the load balancer steps in and becomes a reverse proxy. It receives the encrypted requests from users, decrypts them using its own SSL certificate, which is much easier to manage than individual server certificates, and then forwards the regular HTTP request onto one of our backend servers. This dramatically reduces the load on those servers, improves overall performance, and makes things way simpler when it comes to managing certificates. Okay, so let's talk about SSL, specifically how it works with load balancers. You'll often hear terms like SSL termination and SSL pass-through. They sound similar, but they actually mean different things. With SSL termination, the server itself handles all the encryption and decryption. It's responsible for managing the SSL certificate. This means the server has to do a lot more work. On the other hand, with SSL pass-through, the load balancer takes care of the SSL handshake and decrypting traffic. It then sends unencrypted HTTP requests to the actual backend servers. The key benefit here is that the origin servers don't need their own SSL certificates, which makes scaling much easier. Okay, let's talk about global load balancing. It's all about making sure your website or app is accessible to everyone, no matter where they are in the world. Instead of just spreading traffic within one region, GLB uses DNS. That's how websites get their addresses, to figure out which server is closest and best equipped to handle a user's request. It considers things like the user's location, network speed, and even whether the servers themselves are running smoothly. Basically, it's like having a really smart traffic controller for your online experience. Okay, let's talk about DNS-based load balancing. It's a really clever way to distribute traffic across your servers. Basically, when someone types in a website address like example.com, their computer first asks a DNS server for the IP address associated with the domain. But here's the key: instead of always returning the same IP, DNS can dynamically change which IP address is returned based on things like where the user is located or how healthy each server is. It's a simple way to provide faster access and better availability. Okay, let's talk about how load balancing works in the cloud. Essentially, it's a really smart way to handle lots of traffic without any one server getting bogged down. There are different levels of load balancing. We have layer 4, which just looks at basic connection information and directs traffic efficiently. Then there's layer 7, which is more sophisticated. It understands the content of the requests themselves, so it can make smarter routing decisions. Finally, you've got GSLB, which spreads your traffic across multiple data centers around the world to ensure speed and reliability for everyone. Okay, so let's talk about ADC. They're essentially the smart managers for your applications. Imagine they're sitting in front of all your servers, making sure traffic gets routed efficiently and securely. ADC don't just do basic load balancing like sending requests evenly across multiple servers. They actually understand how each application works, whether it's HTTP/2 or something else, and sends the request to the server that's best suited for it at that moment. They can also direct users to different content based on what they're looking for, handle SSL encryption without burdening your servers, and even offer built-in security features like firewalls and protection against denial of service attacks. Plus, they give you really detailed reports about how your applications are performing. Okay, let's talk about how load balancers really boost high availability. Think of it like this: instead of having all your requests go to just one server, which could be a major problem if that server goes down, a load balancer spreads the work around to several servers. It constantly checks each server to make sure they're healthy, and if one fails, it automatically takes its traffic elsewhere. Having multiple load balancers themselves adds another layer of protection, so even if one breaks, you don't lose service. And for some applications that need to remember where a user was in an app like shopping carts, load balancers can ensure they always connect to the same server for that session. Okay, so let's talk about scaling, how we make our applications handle more users. There are two main ways to do this: vertical scaling and horizontal scaling. Vertical scaling is like upgrading your computer or giving an existing server more power. It's simple at first, but it has limitations. Eventually, you hit a hardware wall and become reliant on one machine. Horizontal scaling is different. It's about adding more machines to the mix. Each new server takes some of the workload, making your application much more resilient and cost-effective in the long run, though setting it up can be a bit trickier. Okay, so let's talk about how auto-scaling fits into the picture of load balancing. Load balancing is all about distributing traffic evenly across your servers to prevent any one server from getting overloaded. Now, auto-scaling is a really clever way to keep things efficient. It automatically adds or removes servers based on how much activity you're seeing. It's constantly monitoring metrics like CPU usage and request rates. When the load goes up, auto-scaling kicks in and spins up new servers using a load balancer. And when the load drops, it scales down again. Basically, auto-scaling uses load balancing to make sure that any newly added servers are quickly integrated into the overall traffic distribution, keeping your application running smoothly as demand changes. Okay, let's talk about the difference between hardware and software load balancers. Hardware load balancers are like specialized servers. They're built specifically for this job and usually deliver really strong performance and reliability. However, they tend to be pricier and less flexible when it comes to changing things up. On the other hand, software load balancers run as programs on regular computers or virtual machines. They're often more affordable, easier to deploy, and you have more control over how they work. Think of them like a versatile tool. But keep in mind that they can sometimes be more resource intensive. Okay, let's talk about some popular options when it comes to load balancers. You'll often hear about Nginx. It's a really versatile tool that can do so much more than just serve web pages. It's excellent at distributing traffic efficiently. Then there's HAProxy, which is built specifically as a powerful load balancing solution, and it has some clever features like keeping track of user sessions. Finally, in the cloud world, Oz Elastic Load Balancing is a big one, with different types to suit various needs. Understanding these basics will be really helpful in your interviews. Okay, so let's talk about how AWS Elastic Load Balancers work. Basically, they're like traffic directors for your web apps. There are a few different types: classic, application, and network, each designed for specific needs. The core idea is simple. When someone tries to reach your application, the ELB smartly distributes that traffic across multiple servers instead of sending it all to one. This prevents any single server from getting overwhelmed and keeps things running smoothly even if one server goes down. It's a really important piece of the puzzle for building reliable applications. Okay, let's talk about AWS load balancers. You'll often see three main types: classic ELB, application load balancer, and network load balancer. The classic ELB is the older generation. It's pretty basic and generally not recommended for new projects. The application load balancer sits higher up in the layers, handling HTTP and HTTPS traffic, which makes it great for modern web apps that need things like content-based routing. Finally, there's the network load balancer, which is super fast, designed for situations where you absolutely need low latency, such as gaming or real-time data processing. Think of each one as having a specific role in your architecture. Okay, let's talk about how Azure Load Balancer and Application Gateway differ. Think of the load balancer as a simple traffic cop. It just directs requests to available servers based on their IP addresses. It's great for ensuring basic high availability for your services. The Application Gateway is much more sophisticated. It understands what you're requesting, not just where it's coming from. It can handle things like routing based on URL or even apply security measures with a built-in web application firewall. Essentially, the ALB provides fundamental load balancing, while the HEW adds intelligence and advanced features for modern web applications.